Hello everyone, so thank you for the introduction. So I'm Guillaume Coeuret Cauquil, so I'm a last year PhD student. And it's a real pleasure for me to be here today to be able to present the work that I did about the inhibition of circular Rydberg atoms decay in the context of quantum simulation. So under the supervision of Igor Dotsenko at the Laboratoire Kastler-Brossel. So to first introduce the big picture in which our experiment takes place. So it's the context of quantum simulation using neutral trapped atoms. So the usual experiments involve single atoms trapped in optical tweezers. And since the neutral atoms don't have really strong interactions, the usual way to do a way to do is to promote them to the Rydberg state, which is a highly excited state, in order to get stronger interactions, which could be of the order of 10 megahertz, and this even at large distances, so the micrometer scale, which means that it allows for possible optical manipulation. In this context, the usual limitations can come from the limited lifetime of the Rydberg states, which is of the order of the 100 microseconds and for one atom. And for example, if you want to scale your system and take, for example, let's say 100 atoms, it goes down to the microsecond scale, which means only like 10 spin exchanges. And here is an example of a simulation performed at Harvard by the team of Michael Lukins, which involves some adiabatic preparation in the beginning, and they said that it's limited basically by the lifetime. So a way to circumvent this issue is to go to the circular Rydberg state, which is a state of maximal angular momentum. And to prepare such states, what we do is that we perform the usual Rydberg excitation by means of lasers. Then we apply a directing field in order to lift the degeneracy between the different M states. And then by means of radio frequency pulses, so we climb this ladder from M equal 2 to 51, basically giving the electron some angular momentum to reach this like a nice circular shape. And at last, once you have your circular state, you may want to like put it into other circular states, which would be your logical qubits. The main advantage of these states is that they have an intrinsic lifetime which is much longer because they don't have direct optical decay channel. And reaching, for example, the tens of milliseconds for 50C at cryogenic temperature. Since we have longer lifetimes, we are we are also limited by the fact that the atoms start to fall, so you have to trap them, and this can be done by means of Fondaire-Motiv effect. But we would like to do better. And to do so, you have to look at what are the main decay channels for the loss mechanisms involved in the loss of your circular state. And it mainly comes from the spontaneous emission from the circular state that is just below. And you might think that's something that is really fundamental, like it's the coupling of the atoms with the vacuum fluctuations, and that it's something that we really can't really have a grasp on. But a proposal by Klepner in the 80s suggested that by changing the surrounding of the atoms, and by this we mean the density of electromagnetic modes, classical, around the atoms, we can decrease the spontaneous emission rate, which means, in our case, longer lifetime. And this can be done by simply putting the atoms in between two planar plates spaced by 2 millimeters. And to study this, you can simulate this with just a classical dipole decay. And what we see is that for circularly polarized light, if you put your dipole in between two plates and you look at the different spacings, when the spacing is below lambda half of the wavelength, you don't have radiation anymore, which would be the case for our atom. However, if it's pi transitions, then it's ENs, but it's something that we can get rid of by going to cryogenic temperatures. Well, this was for an ideal capacitor, so what for a realistic one? A few years ago, my group performed some simulations to estimate what could be the realistic application of this idea. And by taking a plate which is of the order of 10 millimeters, with a spacing of 2 millimeters, we can expect to have some good enough inhibition for what we want to do. To have a more realistic estimation, they also took into account different loss mechanisms, so vacuum or other stuff, and which in the end gave the number that we could expect to have 47 seconds lifetime for a single atom inside a capacitor. And to give just some idea, the minute range lifetime means that if you take, for example, 40 atoms, you will have 1 second, which means up to 10 to the 5 spin exchanges for the kind of simulation you want to perform, which is way larger than what was proposed earlier. Well, so the main goal of my PhD was to design and build such experiments. So for this, what you need is two inhibition plates inside of a cryostat. So you would like also to have some Rydberg excitation to get Rydberg atoms, as well as the means to circularize them. For state measurement, we decided to go for ions detection. And you also would like to have some microwave drive, as I said in the introduction. And you want the atoms to be trapped, so you need a trap. And to place them in between the two plates carefully, we're using it in a conveyor belt fashion to be able to displace the atom out or in between the two plates. And to trap the Rydbergs as well, we need another kind of trap, which is the Lagergos motif trap. And last but not least, we want to trap atoms, so we need cool atoms. And by this, we are using magneto-optical traps. So, well, looks like an easy plan. But the thing is that as soon as you start to look at what a real cryostat looks like, it's a bit more messy. So you have different shields and different chambers, which means that you have a very small optical access. And in addition, if you start to look at the experiment core that we design, you want to have many different elements in a very compact way. In the middle of which you will have a very small region in which you will have the inhibition block. And this, with this, I would just to draw your attention to the fact that the main challenge that we'll have here is that we want to both have a well-isolated system together with a very good control over it. So, well, the first thing that we designed was the experiment core. So it starts pretty easy with the two plates spaced by 2 mm. We took this shape, like here, and for the detection, you need a hole in one of the plates, and for this we design a conic shape such that we disturb as less as possible the geometry of the plates. And we performed also some numerical simulations to make sure that even with this shape we can manage to measure enough number of ions and to direct them in the channeltron. Then for the circularization, we need RF radio frequency electrodes, so which are in between the two plates. All this embedded in some block to hold everything in place, in which you would like to have a hole to perform your Rydberg excitation, as well as another optical access to be able to trap your atoms. And as you can see here, you see again that we have a very small optical access, which made the alignment procedures a bit harder than what we would like. Well, for the magneto-optical trap, similar issues appeared. So for this, you need two elements. So the first one is the good control of a magnetic field. And for this, usually what people can do is that they put large coils outside of the experiment. For us, it's not possible because we want to screen the magnetic field that can come from outside. So we designed small coils in a compact way that we put directly inside of the experiment core. And we decided to take superconducting coil to avoid additional heating inside of the experiment core. Well, for the cooling beams, like similar problem, due to the low optical access, we decided to perform the crossing of the counterpropagating beams directly inside of the cryostat instead of, and not like from outside. And due to the constrained geometry, we had to take smaller beams rather compared to what is usually done, especially along the dipole trap axis, in which we needed to have a beam which is small enough to go in between the two plates. Despite all this, we managed to get an unusual, like state-of-the-art MOT cloud, so with like 10 microkelvin and like 1 million atoms. Well, and which means that we could move to the dipole trap setup, for which we used two counterpropagating beams to create this interferences pattern. So small interferences in which, like small pockets in which the atoms will be trapped. And for this, we have lenses inside of the experiment to directly focus the beam in the core to get a waste of like 10 micrometer. And in order to be able to displace the atom, what we do is that we slightly detune one of the beam, which makes the interferences pattern move, meaning that with this, we have a very good control of the atom's position directly inside of the capacitor. However, the ray length of the trap we have is only 0.3 millimeter because we want it to be tightly focused. And the distance over which we want to move the atoms is 14 millimeter, which is way larger than the ray length, meaning that as soon as you start to transport over a few millimeters, you completely lose your atoms. To counter for this, we needed to move the waist position as well, and for this we used a focus tunable lens outside of a cryostat, and with this we managed to keep a good enough efficiency, this even at large transport distances. Well, to wrap up everything, so currently we managed to design and manufacture the main pieces of the experiment. The atoms cooling and trapping step are okay, and the atoms transport is currently under optimization. The next step would be to perform the Rydberg excitation, detection, circularization, and at last the lifetime measurement. And with this, I would like to thank all the people involved in this work, especially Igor, who supervised me for the last years, the organizers of the conference for allowing me to present my work, and you for your attention.
Thank you very much. Yeah. Questions? Yeah.
Thank you for your talk. So you said that you wanted to simulate very slow processes, and that's why you need a very long lifetime. Could you give us examples of these slow processes that you want to simulate?
For the processes directly, I don't have like a precise example, but the typical kind of model that we can simulate with like typically with this, what we can do is typically a spin chain. And the typical model presented in the paper is the XXZ model. And I think that for this, there are some effects like quantum scars or slow thermalization process that are interesting to look at.
Okay, thank you.
Further questions? Yeah.
How will you reorder your atoms once they are in the trap? Because if you don't have,
For this, the idea was, we have several options, but the first, the main that we have in mind so far is not to like be able to create arbitrary chain, but to just a fully populated chain. And by this, the idea is to put like two beams on both sides orthogonal, so one here and here, for example, and to do a kind of evaporation. So we, with one of the beam, we compress the chain until we reach a regime for which we have all sides populated. And yes, but it's not for an arbitrary population.
Ah, yeah. Yeah. There. The question down there.
Like, would you like? I think that's an interesting mechanism to like inhibit the decay. Would you like briefly explain again about like why does it be inhibited?
Why the
Because of the capacitor.
yeah. So just the beginning. Yeah, it's there. So yeah, for the inhibition, so there is different point of view that you can take to see this. The simple one is to say that basically, if you have an infinite, two infinite plates, it's like a kind of waveguide somehow. And if the spacing is below the wavelength of the the electromagnetic field you look at, simply the electromagnetic wave can't propagate in between the plates, meaning that if the atoms want to emit these waves, it just doesn't occur, because the photons that the atom will emit just won't be emitted. Another way to see this is that the plates, they act as a kind of as a conductive mirrors, and by doing a mirror image analysis of the different stuff, you see that the dipole will create a dipole in opposition phase, and with this on the other side as well, meaning that you will have a chain of dipoles oscillating in a position of phase, meaning that it will, due to destructive interferences, completely destroy the emission that you expect.
Thank you.
I hope it was clear, but
I have a final question. So
yes.
regarding at the end, you have a chain of Rydberg atoms. The loading from the MOT is not a problem because of Rydberg blockade. So typically, you expect to have one atom for each trap, essentially.
And this is not entirely sure, because the waste that we have is 10 micrometer, which is maybe a bit too large for the blockade, for the collisional blockade, to have single atoms really inside. And for the Rydberg station, we can do in a kind of probabilistic way, like putting enough lasers such that we statistically have one atom per site or less, and then by compression making sure that we
Okay, thank you.
have what we want.
If There is no further question. Let's thank all the speakers of this first session of this morning.